2 of functional MRI. So roadmap, today we are mostly digging in on how the signal is turned into images. So part 1 we talked about what is the scanner and what kind of signal it collects, and so today is bullets 2 and 3 here. And okay, so we got the person in the bore of the scanner. The scanner is a really powerful magnet, and we've defined 3 axes. We've got the z-axis going straight down the middle of the bore, and then the x and y axes going perpendicular to the z-axis. All right. So we got to talk about hydrogen atoms. We got to talk about physics. Hydrogen atoms are like little tiny spinning magnets. So here's a picture of a hydrogen atom, and it's got, like any magnet, it's got an orientation, a north and south to it. Unlike your standard magnet, it is spinning really, really fast. In a weak magnetic field, all of the hydrogen atoms, in your brain, are oriented in any which direction. So their magnetic moments, their magnetic orientations are all over the place, variable, not aligned with each other. But when you put the brain, you put the tissue in the scanner in that really strong magnetic field, you get a lot of the protons, the hydrogen atoms in the brain to orient in the same direction. They're more likely to be oriented in the same direction, the direction of the field axis of what we call B0 along that z-axis on the previous slide. So we're going to be talking about the classical physics description of how a scanner works, and this is the super simplified version because it's not a class on functional MRI. It's just a topic that we're digging into a bit to set up our exploration of multivoxel pattern analysis or multivariate pattern analysis. But so the classical physics explanation is that we've got these hydrogen atoms, they're spinning really fast, and if a top was spinning really fast and it wobbled, it does something called precession. I've got a picture of that on the next slide. The idea is that the hydrogen atoms are spinning like tops, and when we pump in this radio frequency pulse that we mentioned in the last chunk, this causes all of those little atoms to precess around the axis of the main magnetic field of the scanner, which produces a signal that we can detect outside of the head. So every atom has a characteristic frequency. So if you bombard it with radio frequency pulses at just this right frequency, the atom will absorb some of that energy and then precess around its spin axis. And this frequency is known as the atom's Larmor frequency. So here we've got a gyroscope precessing. So the classical analogy is that literally the hydrogen atoms are precessing around their spin axis. So there's like you can imagine the main magnetic field going up down here, and this is the hydrogen atom spinning around that axis, or precessing around that axis. Okay, so here we go, a little doodle version. Radio frequency pulse comes in, causes all these atoms to precess, and while the radio frequency pulse causes them to absorb energy, and that exhibits itself as this precession, then they come back into alignment gradually with the main magnetic field. Both of these shifts of getting kicked out of alignment and then gradually coming back into alignment can be detected as induced currents in a coil near the head. So this is called the head coil in the scanner. And the only way that we can do this, that this works, is because the hydrogen atoms are all aligned, so they're all doing the same thing at the same time, and it produces enough of a signal that we can pick it up. And we end up often using the same coil that produces this radio frequency pulse, like a little antenna. It also picks up the induced current. So here we go, our little doodle, radio frequency pulse causes the atoms to absorb energy, and as they realign with the magnetic field of the scanner, they emit a coherent radio frequency signal at this frequency that can get picked up. So the radio frequency pulse is in what's called the VHF range, and if you're of a certain age, you know VHF was the range that the TVs of our childhoods picked up signal using little aerial antennas that were either up on your roof or on top of the TV itself. Different names for the different parts of the radio frequency spectrum. We've got the very high frequency, ultra high frequency, extremely high frequency, tremendously high frequency, which goes from 300 gigahertz up to 3 terahertz. And just for reference, we got visible light is all the way up at 300 terahertz or so. So we're a long way from visible light down in the VHF range with the sorts of pulses that we're sending in. So the Larmor frequency of hydrogen is 63.78 megahertz at 1.5 Tesla. And a key point that we're going to build on over the course of this is that the resonant frequency of a given atom is a linear function of the magnetic field strength. So for hydrogen, it's 42.58 megahertz per Tesla. So if all we had was the static magnetic field of the Bohr called B0, and we pulsed, sent in a radio frequency pulse, all the protons all over the body all at once would all ring. They would all start processing, and they would all come back into alignment, and we would get a signal that would tell us, about how many protons there were. It would be at least sensitive to how many protons there are inside the Bohr, but we wouldn't be able to tell which protons are located where, and we need to know that to turn this into an actual image. So the solution, there's a ton of clever things that are done in with the scanner technology, but one of the first clever ones here is that you can add a gradient to the magnetic field so that along that z-axis through the Bohr, that at different planes along the z-axis, there's a different magnetic field strength, which means that the hydrogen atoms at one place versus another are going to have different resonant frequencies. So you can target just a particular Z plane passing through the brain. I got a little picture of that. So here's our Bohr. Imagine the person's in there. We've introduced a gradient onto the main magnetic field of the scanner such that along the Z-axis it's getting stronger in one direction, weaker in another direction. And then we can send in a radio frequency pulse that targets a particular plane along that z-axis because of this idea of how the resonant frequency of the protons scales with the magnetic field strength. So now there's a couple of details coming up here that I'm going to blur over exactly how it works because it just gets way too involved for this class. The summarized version is okay, so you start off by putting a gradient along the z-axis to select a particular slice. You pulse with radio frequency to excite the protons in that slice, and then immediately after that you add 2 more gradients along the x-axis and the y-axis of the scanner, and these get manipulated in a way that causes the induced current that you pick up at the head coil to reflect certain spatial properties of the distribution of protons in that slice of brain. So this technique is called phase encoding, and again, I'm just going to try and give you a rough sense of how it works and put some references in the doodly-doo below the video that you might want to check out to learn some more about this. But the idea is that we're able to actually directly measure, from these resonant signals coming off the brain, a spatial Fourier transform of the image, of the tissue that's in the Bohr. With the idea being that at particular time points, the intensity of the signal indicates the convolution of a particular sinusoidal grating with an image on the xy plane. And this I'm going to dig into. with some figures coming up. But just wanted to say that this is one of the more advanced topics in magnetic resonance image formation, and there are other courses here at Vanderbilt that you could take, or resources that you could go read to learn a lot more about this, but I'll just give you the basics. All right, so the one basic idea is that any sort of signal, like a time course or an image, regardless of how complex it seems, can be broken down into simpler components. And so here's a very simple example using three sine waves and showing that you can add these sine waves together to create a more complicated looking sine wave. And the idea is that you could create any sort of time course here. You could break it into actually a set of sine waves of different phases and amplitudes and frequencies. You could make a step function. You could make any sort of curvy thing that you want. And the neat thing is that you can do this in 2D as well, so for 2D images. So these are called sinusoidal gratings, and they can vary in spatial frequency, orientation, and phase. So spatial frequency is how many bands you get across the image. So this is a lower spatial frequency, this is a higher spatial frequency, this is an even higher spatial frequency. You can see how each of these three gratings is oriented differently. And then the phase would just shift the dark and light patch one way or another. And the idea is that any image that you can, any grayscale image here that you can come up with, you can approximate with some, might be a rather large number of these gratings, but here's an example of how complicated you can get with just three, and you've got this sort of cool little pattern here. And this is literally, I found some code from Yuki Kamitani on GitHub to generate these sinusoidal gratings, and then really just added them together pixel by pixel to get this image down below. All right. So, we can, if we have enough of these bands and we add them together, we can approximate any two-dimensional image. And I said, here's our example. All right, so you remember this part where we've got all of these protons processing and emitting their signal as they are realigning with the magnetic field. So we got to take that part of the story and link it up with this part of the story. What do these bands have to do with the radio frequency signal that comes out of the brain when you pulse it with RF? So imagine that you took one of these bands, one of these gratings, and you could superimpose it on, a slice of the brain that happens to be just at that z-axis, that point in the z-axis that you're ringing. You could calculate how much the light pixels in the image line up with the white parts of these bands, and which is actually what the scanner ends up doing. So that thing I said about manipulating the X and Y magnetic gradients, it actually alters, it creates a pattern like this across that Z-plane that we talked about, and the frequency and the orientation of these bands is being changed very quickly, and the signal coming out of the scanner reflects the amplitude of this. This is called a component. It's how many, and the amplitude of the component is going to reflect how much of the white stuff here in the brain matches up with the white parts of the grating. And so if you do this with enough different gratings, you end up being able to perfectly, recover to whatever degree of precision you have time for the image of the tissue that's in at that particular slice of the Z plane. So, all right, so here's the last bit. I wanted to show you a real example, and I found this nice article released via Creative Commons on PubMed Central. It was a tutorial on how K-space works, and I put the details down at the bottom there. So this is an example of how this spatial decomposition process works, but this is using an MR image of a heart, a heart with a defect in it. And here's a good way to look inside that heart without cutting it open. So the left-hand boxes depict. All right. So one thing to say is that the left-hand and the right-hand images, they're both the same image. But how could that possibly be? What does that even mean? Like, one of them looks like a little starburst, the other looks like you cut through a heart. Well, the picture on the left is the same image, but in terms of something called K-space. And K-space is a way of organizing all of those different spatial gratings that we were just looking at on the previous slides. And so each point in this left-hand image represents one of those gratings, where the closer you are to the center, the lower frequency, the more coarse the grating is. The further away you get, the more sharp, the more high frequency the grating is. And the angle from the origin here in the middle tells you what the orientation of the bars are. And the color of the pixel tells you what the amplitude of that component is. So this image of the heart on the right is all the information you need is actually in this image on the left to reconstruct this rather sharp-looking anatomical scan. And just to give you a little more concrete idea of an example of what's going on, if you snipped out all of the information, outside of a certain radius from the center, you're just keeping those low frequency spatial bands. So you just have the low frequency bands left, but you still have, a lot of them and a lot of different orientations, and you can still create a blurry image. You can still reconstruct a blurry image, even though you lost a lot of data that you had in panel A from panel B. Panel C shows you what you do if you get rid of the low frequency stuff and just keep the high frequency information. And you can see that it retains the higher spatial frequency components of the images, like the edges and stuff. So just to recap, each point in this K-space corresponds to a spatial grating with a particular frequency and orientation. The value of the pixel at that point reflects the amplitude of that grating. Right, so these are just the left-hand image and the right-hand image are just two different ways of presenting the same information. But, we can't just look at the left-hand one and tell that it's a heart, but it is. So, yeah, like I said, panel B just cuts out the high frequency stuff, leaving you the fuzzy low frequency stuff. Panel C cuts out the low frequency stuff, leaving you with the sharp high frequency stuff.